machine learning questions that foreign interviewers really care about. How does pruning improve a model's performance? Answer: pruning helps improve a model's performance by removing splits that have little impact, which allows the model to focus on more significant attributes. This enhancement in performance is achieved by reducing the complexity of the model and eliminating unnecessary information, making it more efficient and accurate. What is the benefit of optimizing computational efficiency in a model? Answer: optimizing computational efficiency in a model decreases its complexity, which can lead to faster training and prediction times. This is because there are fewer nodes to traverse during decision-making, making the model more efficient in its calculations. This can be particularly important in situations where speed and accuracy are crucial, such as in real-time applications or when dealing with large data sets. How does random forest ensure diversity among the trees in the model? Answer: random forest ensures diversity among the trees in its ensemble through two main mechanisms. First, it uses a random subset of features at each split, which prevents any one feature from dominating the model. Second, it uses bootstrap sampling to create each tree, which ensures that each tree is trained on a different subset of the data. This combination of random feature selection and bootstrap sampling helps to create a diverse set of trees that can collectively make accurate predictions. By combining the predictions of these diverse trees, random forest is able to reduce overfitting and improve its overall performance. What is bootstrap aggregating bagging in random forest, and how does it contribute to the decision-making process? Answer: bootstrap aggregating bagging is a technique used in random forest, where each tree is trained on a different bootstrap sample, which is a random subset of the data. This means that each tree sees different portions of the data, leading to variations in their learning and decision-making processes. This variation helps to reduce the correlation between trees, making the overall prediction more robust and accurate. By combining the predictions of multiple trees, the random forest model can make more informed decisions, as the variations in individual trees are averaged out. This approach helps to improve the model's performance by reducing overfitting and increasing its ability to generalize to new, unseen data. What is the purpose of feature randomness in random forest, and how does it affect the model's performance? Answer: feature randomness in random forest is a technique where a random subset of features is selected for each split in the tree. This ensures that trees do not follow the same paths or use the same splits, increasing the diversity among the trees. This diversity reduces the variance of the model without significantly increasing the bias, resulting in a more accurate and robust model. In other words, feature randomness helps to reduce overfitting and improve the overall performance of the model by creating a more diverse set of trees. What is information gain, and how does it help in creating a decision tree? Answer: information gain is a measure used in decision trees to select the best feature that splits the data into the most informative subsets. It calculates the reduction in entropy or impurity after a dataset is split on an attribute. This helps guide the creation of the tree structure by identifying the most informative attribute to split the data, which in turn reduces the randomness or uncertainty in the dataset. By choosing the attribute with the highest information gain, the decision tree can make the most accurate predictions and classify the data effectively. How does the independence assumption affect the accuracy of a naive Bayes classifier? Answer: the independence assumption in a naive Bayes classifier simplifies the computation of a probability model by allowing the calculation of the conditional probability of the class given multiple features as the product of individual probabilities for each feature. This assumption can lead to inaccurate results if the features in the dataset are not truly independent, as it ignores any dependencies or correlations between the features. Therefore, the accuracy of a naive Bayes classifier can be affected negatively if the independence assumption is not met, resulting in overfitting or underfitting of the model. On the other hand, if the features are truly independent, the independence assumption can lead to more accurate results. However, in real-world datasets, features are often correlated, making it essential to consider alternative models that can handle dependencies between features. What are the strengths of the independence assumption in high-dimensional data, and how does it perform in practice? Answer: the independence assumption can sometimes lead to good performance in high-dimensional settings such as text classification, despite the interdependencies among features. This is because the errors in probability estimates may cancel out across the large number of features, resulting in acceptable results. In other words, the assumption of independence can work well in high-dimensional data because the errors in probability estimates are averaged out, leading to a good overall performance. What are the limitations of naive Bayes when features are not independent, and how does it affect the model's performance? Answer: naive Bayes can be inaccurate when features are not independent because it assumes that each feature is independent of the others. If features are strongly dependent and critical to predicting the class, the model may underperform because it fails to capture the interactions between features. This limitation can lead to reduced accuracy and poor performance of the model. What is the generalization capability of naive Bayes, and how does it perform on smaller datasets or with limited training data? Answer: naive Bayes has a generalization capability that allows it to perform well on smaller datasets or with limited training data due to its simplistic nature. This is because the independence assumption in naive Bayes does not require a complex model like other classifiers, making it a suitable choice for situations where data is limited. As a result, naive Bayes can still achieve good results even with a small amount of training data, making it a useful and efficient classification algorithm. Why does PCA maximize the variance in the data? Answer: PCA maximizes the variance in the data because variance represents how much information is spread out in a given direction. By focusing on the directions of highest variance, PCA helps us preserve information while reducing dimensionality and simplify the data by eliminating less important features, those with low variance. In other words, PCA aims to capture the most important patterns and relationships in the data by maximizing the variance, which allows us to understand and analyze the data more effectively. How do you evaluate the effectiveness of a machine learning model in an imbalanced dataset scenario, and what metrics would you use instead of accuracy? Answer: to evaluate the effectiveness of a machine learning model in an imbalanced dataset scenario, we can use metrics such as precision, recall, phone score, and ROC. The phone score is considered the best metric as it combines both precision and recall into a single metric, which is important in imbalanced datasets where a high number of true negatives can skew accuracy. The phone score ensures that both the positive class detection and false positives are accounted for. If the cost of false positives and false negatives is similar, the phone score strikes a good balance. It is especially useful when prioritizing performance in detecting the minority class. However, if false positives or false negatives are more costly, we can opt for precision or recall respectively. How does the one-class SVM algorithm work for anomaly detection, given that only normal data is available? Answer: the one-class SVM algorithm is an unsupervised anomaly detection method that learns a decision boundary around normal data points using a kernel, typically an RBF, to map the data into a higher dimensional space. It identifies support vectors, which are data points closest to the boundary, and any new data point outside this boundary is flagged as an anomaly. The algorithm's performance is controlled by parameters like new, which determines the fraction of outliers allowed, and the kernel, which defines the boundary shape. This approach allows the algorithm to effectively detect anomalies in data where only normal data is available. What is concept drift in anomaly detection, and how does it affect anomaly detection models? Answer: concept drift refers to the change in the underlying distribution or patterns in the data over time. This means that what was previously considered normal data may become abnormal over time. In anomaly detection, this is a challenge because a model trained on old data may not recognize new following patterns as part of the normal data distribution. This can cause previously normal data points to be incorrectly identified as anomalies. To address this, models can be adapted through periodic retraining with new data or by using adaptive anomaly detection algorithms. This helps the model to learn the new patterns and avoid false alarms. What are the different types of kernels used in support vector machines SVM? Answer: in support vector machines SVM, there are 6 types of kernels used to transform the input data into a higher dimensional space. These kernels are linear kernel, polynomial kernel, radial basis kernel, sigmoid kernel, and others. Each kernel is used in specific situations, such as when the data is linearly separable, linear kernel, when the data has no natural notion of smoothness, polynomial kernel, or when a decision boundary needs to be created to separate 2 classes, radial basis kernel. Understanding the different types of kernels is crucial for selecting the right one for a particular problem and achieving accurate results. Why was machine learning introduced? Answer: machine learning was introduced to make our lives easier by enabling systems to learn from data and identify patterns, eliminating the need to write new rules for each problem. This approach allows for more efficient and effective processing of data, making it possible to automate tasks and make decisions without human intervention. The concept of machine learning was first proposed by Alan Turing in his 1950 paper Computing Machinery and Intelligence, where he asked the question, can machines think, and introduced the idea of the imitation game to test the ability of machines to mimic human thought and behavior. What is the main difference between classification and regression in machine learning, and how do they differ in their applications and outputs? Answer: the main difference between classification and regression is the type of output they produce. Classification is used to predict discrete or categorical results, such as classifying emails as spam or non-spam, or predicting whether it will be hot or cold tomorrow. On the other hand, regression is used to predict continuous or numerical results, such as predicting stock prices or temperatures. While classification is used to assign data to a specific category, regression is used to model the relationship between variables and make predictions about continuous outcomes. This difference in output type has significant implications for the applications and use cases of each technique, with classification being particularly useful for tasks such as image recognition, sentiment analysis, and recommendation systems, and regression being more suitable for tasks such as forecasting, prediction, and modeling continuous phenomena. What is bias in machine learning, and how can it affect the results of a machine learning model? Answer: bias in machine learning refers to the unfair or inaccurate treatment of certain groups or individuals in the data used to train a model. This can occur when the data is inconsistent or incomplete, leading to incorrect predictions or decisions. For example, if a hiring algorithm is trained on a data set that is biased towards hiring men, it may produce results that are not gender neutral. To mitigate bias, machine learning models can be tweaked or retrained on more diverse and representative data to produce fairer results. What is cross-validation? Answer: cross-validation is a data splitting technique where a data set is divided into k subsets, and a model is trained on k-1 subsets, while the remaining subset is used for testing. This process is repeated for each subset, and the scores from all k-folds are averaged to produce the final score. This method helps to evaluate the performance of a model by reducing overfitting and providing a more accurate estimate of its generalization ability. What are support vectors in SVM? Answer: in the support vector machine SVM, support vectors are the points that lie on the edge of the dividing hyperplane between different classes. These points are crucial in determining the optimal separation between classes, as the SVM algorithm tries to maximize the distance between the hyperplane and these points. In other words, the support vectors are the most important data points that help the SVM algorithm to make accurate predictions. They are also the points that are closest to the decision boundary, making them the key to the SVM ability to classify new data points effectively. What is support vector machine SVM and how does it classify data? Answer: a support vector machine SVM is a powerful supervised machine learning model that can perform linear or non-linear classification, regression, and even outlier detection. It works by viewing data points as p-dimensional vectors, then trying to separate them with the p-1-dimensional hyperplane. The goal is to find the best hyperplane that represents the largest separation or margin between the two classes. This is known as a maximum margin hyperplane, and the linear classifier it defines is called a maximum margin classifier. SVM is particularly useful when the data is not linearly separable, as it can find a non-linear boundary to separate the classes. In essence, SVM tries to find the best hyperplane that maximizes the distance between the two classes, making it a robust and effective classification algorithm. What is the equation of the hyperplane H3 and what does the parameter B represent in the equation? Answer: the equation of the hyperplane H3 is W, xb equals 0, where W is the normal vector of the hyperplane. The parameter B represents the offset of the hyperplane from the origin along the normal vector W. It determines how far the hyperplane is from the origin in the direction of the normal vector. If B is positive, the hyperplane is above the origin, and if B is negative, the hyperplane is below the origin. The parameter B is proportional to the distance of the hyperplane from the origin, with a larger value indicating a greater distance. What is the condition for X in the context of support vector machine SVM? Answer: in the context of support vector machine SVM, X satisfies the condition W. Roman 11b equals 1 or W. Roman 11b equals -1, where W is the weight vector, Roman 11 is the input vector, and B is the bias. This condition defines the hyperplane that separates the classes in the feature space. The points that satisfy this condition are called support vectors. They are the points that are closest to the hyperplane and are used to define the decision boundary. What is principal component analysis (PCA) and when is it typically used? Answer: principal component analysis (PCA) is a dimension reduction technique used to simplify complex datasets by identifying the most important features or variables. It is typically used when there are many variables in a dataset and we want to reduce the number of variables while retaining most of the information. This is particularly useful when there are linear correlations between features, as it can help to identify the underlying patterns and relationships in the data. PCA is commonly used in finance, neuroscience, and pharmacology, among other fields, as a preprocessing step to make datasets easier to visualize and analyze. What does the term naive refer to in the context of naive Bayes? Answer: the term naive in naive Bayes refers to the assumption that all attributes features are independent of each other. This means that the algorithm simplifies the complex relationships between features by assuming that each feature is independent and can be considered separately. This simplification allows the algorithm to make predictions more efficiently, but it may not always be accurate in real-world scenarios. What is unsupervised learning? Answer: unsupervised learning is a type of machine learning algorithm that is used to find patterns in a given set of data without having a dependent variable or label to predict. It is a self-organizing process where the algorithm groups similar data points together or identifies unusual data points without any prior knowledge of the expected output. This type of learning is commonly used in applications such as clustering, anomaly detection, and neural networks with latent variable models. For example, in image recognition, unsupervised learning can group similar images together based on their features such as color, texture, and shape. What is supervised learning? Answer: supervised learning is a type of machine learning where a computer is trained on labeled data to make predictions while classifying new unseen data. In supervised learning, the training data is already labeled with the correct output, which helps the algorithm learn to map inputs to outputs. This process allows the algorithm to make accurate predictions or classifications on new data. For example, in the context of the t-shirt classifier, the labeled data would include examples of S, M, and L t-shirts, which the algorithm would use to learn how to classify new t-shirts into these categories. What are the different types of machine learning algorithms, and how are they categorized? Answer: machine learning algorithms are categorized into three main types: supervised, unsupervised, and reinforcement learning. Supervised learning algorithms are trained with labeled data, where the correct output is provided for each input. They learn to make predictions by minimizing the error between their predictions and the actual output. Examples of supervised learning algorithms include linear regression, decision trees, and neural networks. Unsupervised learning algorithms, on the other hand, are trained with unlabeled data and learn to identify patterns or structure in the data. Examples of unsupervised learning algorithms include k-means clustering, hierarchical clustering, and principal component analysis. Reinforcement learning algorithms learn by interacting with an environment and receiving rewards or penalties for their actions. They aim to maximize the cumulative reward over time. Examples of reinforcement learning algorithms include Q-learning, SASA, and deep Q networks. These categories are not mutually exclusive, and many algorithms combine elements from multiple categories. What is the phone score and how is it used in binary classification? Answer: the phone score is a measure of a model's accuracy in binary classification, calculated as the harmonic mean of precision and recall. It's a weighted average of precision and recall scores, which helps to balance the two. The phone score is used to evaluate how well a model retrieves relevant results in information retrieval tasks, with scores ranging from 0 worst to 1 best. It's a useful metric to assess the performance of a model in detecting relevant instances, taking into account both precision avoiding false positives and recall avoiding false negatives. What do precision and recall measure in the context of machine learning, and how do they differ? Answer: precision measures the proportion of items that are truly relevant among those predicted to be relevant by the classifier, whereas recall measures the proportion of truly relevant items that are correctly identified by the classifier. In other words, precision answers the question out of the items that the classifier predicted to be relevant, how many are truly relevant, and recall answers the question out of all the items that are truly relevant, how many are found by the classifier. Both metrics are important in evaluating the performance of a machine learning model. How do we handle overfitting and underfitting in machine learning models? Answer: overfitting occurs when a model is too complex and fits the training data too well, resulting in poor performance on new and seen data. To tackle overfitting, we can use techniques like k-fold cross-validation to estimate the model's accuracy. On the other hand, underfitting occurs when a model is too simple and fails to capture the patterns in the data. To handle underfitting, we can change the algorithm or add more data points to the model. By understanding and addressing these issues, we can improve the performance and generalizability of our machine learning models. What is a neural network? Answer: a neural network is a simplified model of the human brain that mimics its structure and function. It consists of interconnected neurons, which are similar to the brain's neurons that process and transmit information. The connections between neurons, called synapses, allow information to flow from one neuron to another, enabling the network to learn and make decisions. This architecture is inspired by the way the human brain processes information, making neural networks a powerful tool for machine learning and artificial intelligence applications. What is the difference between a loss function and a cost function in machine learning? How do they relate to each other? Answer: a loss function is used to measure the difference between the actual and predicted values for a single data point, whereas a cost function is used to calculate the sum of errors for multiple data points. In other words, a loss function is used to evaluate the performance of a model on a single record, while a cost function is used to evaluate the performance of a model on the entire training dataset. The most commonly used loss functions are mean squared error and hinge loss, while the most commonly used cost function is the sum of the fixed costs and the variable costs. The key difference between the two is that a loss function is used to calculate the error for a single data point, while a cost function is used to calculate the total error for the entire dataset. What is ensemble learning and why is it used in machine learning? Answer: ensemble learning is a method in machine learning that combines multiple machine learning models to create a more powerful model. This is done to achieve a balance between bias and variance, which is known as the bias-variance trade-off. The different models used in ensemble learning can be created using different populations, hypotheses, or modeling techniques. By combining these models, ensemble learning helps to reduce the error in the model, which can include bias, variance, and irreducible error. There are two main methods of ensemble learning: bagging and boosting, which are used to optimize the weighting scheme for the training set. Ensemble learning is used to improve the accuracy and robustness of machine learning models. How do you determine which machine learning algorithm to use for a given dataset? Answer: to determine which machine learning algorithm to use, you need to perform exploratory data analysis (EDA) on the dataset. This involves classifying variables as continuous, categorical, and so forth, summarizing variables using descriptive statistics, and visualizing variables using charts. By doing so, you can gain insights into the dataset and select the best fit algorithm based on the characteristics of the data. For instance, if the data is discrete, you may use SVM, while continuous data may be suitable for linear regression. The EDA process helps you interview the dataset and make an informed decision about which algorithm to use. How would you handle outlier values in a dataset? Answer: outlier values can be handled in 3 simple strategies: dropping them, marking them as outliers and including them as a feature, or transforming the feature to reduce the effect of the outlier. This is because outliers can significantly affect the analysis and interpretation of the data. By handling outliers, we can ensure that our results are more accurate and reliable. For instance, if we are analyzing the average height of a population, an outlier of an extremely tall person can skew the average height, making it less representative of the population. By dropping or transforming this outlier, we can get a more accurate representation of the population's average height. Similarly, marking outliers as a feature can help us identify and understand the characteristics of these outliers, which can be useful in certain situations. Ultimately, the strategy chosen to handle outliers depends on the specific context and goals of the analysis. What is a random forest and how does it work in machine learning? Answer: a random forest is a machine learning method that combines multiple decision trees to make predictions. It works by randomly selecting a subset of features from the training data and using these features to create each tree. The trees are then combined to produce a final prediction. The random forest algorithm starts by selecting a random sample of the training data and then recursively splits the data into smaller subsets based on the most important features. This process is repeated until a stopping criterion is met, such as a minimum number of observations in a node. The final prediction is made by taking the average or majority vote of the predictions from each tree. Random forest is a powerful and versatile algorithm that can be used for both regression and classification tasks. It is known for its ability to handle high-dimensional data and to be resistant to overfitting. What is the difference between collaborative filtering and content-based filtering in recommendation systems? Answer: collaborative filtering is a type of recommendation system that predicts new content by matching the interests of an individual user with the preferences of many users. On the other hand, content-based filtering is a type of recommender system that focuses only on the preferences of the user, making new recommendations from similar content according to the user's previous choices. In other words, collaborative filtering considers the collective opinions of many users, while content-based filtering relies solely on the user's individual preferences. This difference in approach can lead to varying levels of accuracy and effectiveness in providing personalized content recommendations. What is clustering and how does it work? Answer: clustering is a process of grouping a set of objects into a number of groups, where objects within the same cluster are similar to each other and dissimilar to those in other clusters. This is done by identifying patterns and relationships among the objects and then dividing them into clusters based on these similarities and differences. There are different types of clustering algorithms, such as hierarchical, k-means, density-based, and fuzzy clustering, each with its own strengths and weaknesses. Clustering is widely used in various fields, including data mining, machine learning, and pattern recognition, to identify hidden patterns, classify data, and make predictions. How can you select the optimal value of k for k-means clustering? Answer: there are 2 common methods to select the optimal value of k for k-means clustering: direct methods and statistical testing methods. Direct methods involve using the elbow method and silhouette analysis, while statistical testing methods involve using gap statistics. The silhouette method is the most widely used method for determining the optimal value of k. It calculates the ratio of the distance between a data point and the nearest cluster center to the distance between the data point and the farthest cluster center. A high silhouette score indicates that the data point is well separated from other clusters, while a low score indicates that the data point is close to other clusters. By analyzing the silhouette scores for different values of k, you can determine the optimal value of k that results in the most well-separated clusters. What are recommender systems? Answer recommender systems are computer programs that help predict what a user might like or want, and then suggest products, movies, music, or other items that are likely to interest them. They use data from various sources, such as user ratings, search queries, or purchase histories, to make these predictions and provide personalized recommendations. This helps users discover new things they might enjoy, and also helps businesses promote their products to the right audience. How do you check the normality of a dataset? Answer: there are several ways to check the normality of a dataset. Visually, we can use plots to identify if the data follows a normal distribution. Additionally, we can use statistical tests such as Shapiro-Wilk test, Anderson-Darling test, Martinez-Iglewick's test, Kolmogorov-Smirnov test, and D'Agostino-Skewness test to determine if the data is normally distributed. These tests provide a numerical value that indicates the probability that the data follows a normal distribution. If the p-value is below a certain significance level, usually 0.5, we can reject the null hypothesis that the data is normally distributed. Otherwise, we cannot reject the null hypothesis, and we can assume that the data is normally distributed. Can logistic regression be used for more than two classes? Answer: logistic regression, by default, is a binary classifier and can only be used to classify data into two classes. However, it can be extended to solve multi-class classification problems, also known as multinomial logistic regression, which allows it to handle more than two classes. This extension is necessary because logistic regression is based on the principle of maximum likelihood, which is not directly applicable to more than two classes. By using techniques such as 1 vs all or 1 vs 1, logistic regression can be adapted to handle multi-class classification problems. What is the difference between correlation and covariance, and how do they measure the relationship between two variables? Answer: correlation is a measure of the strength and direction of the relationship between two variables. It ranges from -1 perfect negative correlation to 1 perfect positive correlation, with 0 indicating no correlation. Covariance, on the other hand, is a measure of the average difference between the values of two variables. While covariance can be used to measure the relationship between two variables, it has the limitation that it is difficult to compare without normalization. Correlation is a more intuitive and widely used measure of the relationship between two variables, as it provides a standardized value that can be easily compared across different datasets. For example, a correlation coefficient of 0.5 indicates that the two variables are moderately related, whereas a covariance of 10 indicates that the variables are related, but the magnitude of the relationship is difficult to interpret without additional context. What is a p-value, and what does it represent in a hypothesis test? Answer: a p-value is the minimum significant level at which we can reject the null hypothesis in a hypothesis test. It represents the probability of observing a result as extreme or more extreme than the one we obtained, assuming that the null hypothesis is true. In other words, it's the probability of getting a result as unlikely as the one we got if the null hypothesis is correct. The lower the p-value, the more likely we are to reject the null hypothesis, as it suggests that the observed result is unlikely to occur by chance if the null hypothesis is true. This helps us make a decision about whether to accept or reject the null hypothesis. What are parametric and non-parametric models, and how do they differ in terms of predicting new data? Answer: parametric models are limited in the number of parameters they can take, and to predict new data, you only need to know the value of these parameters. Non-parametric models, on the other hand, have no limits on the number of parameters, allowing for more flexibility. To predict new data, you need to know the state of the data and the model parameters. This means that parametric models are more restrictive, while non-parametric models are more flexible and can capture more complex relationships in the data. What is reinforcement learning? Answer: reinforcement learning is a type of machine learning where an agent learns to make decisions by interacting with an environment and receiving rewards or penalties for its actions. Unlike supervised and unsupervised learning, reinforcement learning does not provide the agent with labeled data or a specific goal, but instead, the agent learns through trial and error by exploring the environment and receiving feedback in the form of rewards or penalties. The goal is to maximize the rewards and learn the optimal policy to achieve a desired outcome. This type of learning is commonly used in applications such as robotics, game playing, and autonomous vehicles. What is the main difference between the sigmoid and softmax functions in machine learning? Answer: the sigmoid function is used for binary classification, where it outputs a probability between 0 and 1 for a single class. On the other hand, the softmax function is used for multi-class classification, where it outputs a probability distribution over multiple classes. The main difference is that the sigmoid function only outputs a single probability, whereas the softmax function outputs a set of probabilities that sum up to 1, indicating the relative likelihood of each class. This allows the softmax function to handle multiple classes, whereas the sigmoid function is limited to binary classification. What is the issue with the probabilities when using the softmax function for multi-classification? Answer: when using the softmax function for multi-classification, the probabilities do not sum up to 1, resulting in a sum of not n, not a number. This is because the softmax function is applied element-wise to the input values, and the resulting probabilities may not be properly normalized. As a result, the sum of the probabilities may not be equal to 1, which is a fundamental requirement in probability theory. This issue can be addressed by normalizing the output of the softmax function or using a different activation function that ensures the probabilities sum up to 1. What is the trade-off between bias and variance in machine learning, and how can we achieve a good balance between the two? Answer: the trade-off between bias and variance refers to the balance between the simplicity of a model low variance and its ability to fit the training data low bias. A model with high bias is too simple and may not capture the underlying patterns in the data, while a model with high variance is too complex and may overfit the training data. To achieve a good balance, we need to find the right number of parameters in our model, which is a trade-off between simplicity and complexity. If our model is too simple, it may have high bias and low variance, while if our model has too many parameters, it may have high variance and low bias. By adjusting the number of parameters, we can find the optimal balance between bias and variance, which is essential for building accurate and generalizable machine learning models.